Hi, this is Mrs. Doris. This is lesson 4-3 entitled Patterns and Nonlinear Functions. Our objective today is that you will be able to identify and represent patterns that describe nonlinear functions. The reason that we are studying nonlinear functions is because some real-life problems are not linear in nature. For instance, bacteria growth grows at an exponential rate. Area and volume also are not linear in nature. Our essential understanding is that just like linear functions, nonlinear functions can be represented using words, tables, equations, sets of ordered pairs, and graphs. All right, here's a picture. This is from your textbook in this lesson, and there are some examples that I'd like you to sketch in your notes. First of all, linear functions. Linear functions can increase as x increases from left to right, meaning that it has a positive slope to it. Linear equations can also decrease as x increases, then y decreases. And linear functions can also have a constant rate. Nonlinear functions can appear in several shapes. However, these are some that you will see. For instance, this one is quadratic in nature, and we will study quadratic equations later this year. Quadratic implies that there is an x squared term in the equation. The next figure is a cubic function. Cubic implies there is an x cubed in the equation for the function. And the last one is an absolute value. If it makes a V shape, then it is an absolute value function. All right, we're going to look at several examples of these. Okay, so here we go. We have a table with x and y, and the first thing that we're going to do is graph the points to determine if it's linear or nonlinear. So let's see, we have our x and our y. I don't believe I can get up to 16 on the vertical axis, so I'm going to go by 2's. So this will be 4, 6, 8, 10, 12, 14, 16. Okay, and on the vertical axis I'll just go by 1's. Each square will represent 1. Okay, so graphing these points, we have 0, 12, 1, 13, which would be kind of in the middle, 2, 14, 3, 15, and 4, 16. All right, if you look at these lines, I'm going to join them with a different color. This is linear. All right, so this is a real good example of a linear function. Let's look at the first difference between our y values. To get from 12 to 13, we would have to add 1. To get from 13 to 14, we're adding 1. To get from 14 to 15, we're adding 1. And to get from 15 to 16, we're adding 1. Notice that our x is always increasing by 1. When the first difference is the same, then we will have a linear function. This implies that we've got y equal to whatever our change is. In this case it's 1. It would be y equals 1 times x, or simply y equals x. Now, I didn't provide a different table here, so I'm going to erase this part, and I'm going to use this table now to represent my x. Well, actually, I don't think I need to worry about that because over here, y is equal to x. This would make x 0. How do I get from 0 to 12? How do I get from 1 to 13? How do I get from 2 to 4? What do I have to do to 3 to get to 15? And what do I have to do to 4 in order to get 16? And I think you will agree that in all cases we have to add 12 to the x in order to get the y. So our equation becomes y equals x plus 12. All right, and there is our final equation for this graph. All right, let's look at the next graph. In this case, let's graph our points first. And this time, because I have some negative y's, I'm going to draw my axes in this way. This is going to be my x-axis up here. This will be my y-axis here. So, plotting my points, I have 0, 0, 1, negative 1, 2, negative 4, 3, negative 9. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. And 4, negative 16. So here's negative 10, 11, 12, 13, 14, 15. Off the graph, but it'd be right there. Okay, as I join these points, and it's going to continue on in this direction, you can see that this is not exactly linear. It has a curve to it. So this is a non-linear function, and we're going to attempt to write an equation for this set of ordered pairs. So let's take a look at our first difference. To get from 0 to negative 1, you would subtract 1. To get from negative 1 to negative 4, you would subtract 3. To get from negative 4 to negative 9, you're subtracting 5. And to get from negative 9 to negative 16, you are subtracting 7. Notice these are not the same. So this right here tells us that it is not a linear function. So let's find our second difference. Our second difference, to get from negative 1 to negative 3, that would be subtracting 2. Negative 3 minus 2 gives us the negative 5. And to get from negative 5 to negative 7, we're subtracting 2. All right, here our second differences are the same. And this implies that it is quadratic. Quadratic means that as we write our equation, it's going to look something like this. Y equals x squared. Okay, now that may not be our equation. In fact, we're going to take a look at this equation and see what we have to do to it to change it in order to make it work for our table. So I'm going to take this away, and I'm going to use my first difference column now to represent my x squared column. So let's take my x and square it. 0 squared is 0. Now I'm going to square the 1. 1 squared is 1. 2 squared is 4. 3 squared is 9. And 4 squared is 16. Well, look at our y's, and let's compare these two columns. Comparing y with x squared, it appears that in the first case, I do get my y, 0, 0. In the next case, what I really need is to make that 1 negative. And in the next case, I need to make my 4 negative. And in this case, I need to make my 9 negative in order to be like my y. And in the case of 16, I need to make it negative. So this implies that I need to multiply x squared by negative 1. That will give me then the negative y that I'm looking for. And of course, in the case of our 0 here, negative 1 times 0 is simply still 0. So this equation can be written, y is equal to negative x squared. And notice I don't need to show the 1 in there. Negative 1 times x squared is simply negative x squared. Okay, so this is not only nonlinear, but quadratic in nature because of the x squared term. Okay, looking at our next table, first of all, we're going to graph it. So this will be my x, this will be my y, and we'll just make every square 1 unit. So we have 0, 1, 1, 2, 2, 5, and I'm going to 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We're going to give some numbers to our graph so we can kind of follow along. All right, 2, 5 is graphed, 3, 10, and 4, 17 is going to be about right here. So again, as I graph it, you'll see that it is not linear in nature, so we're going to call it nonlinear. And next we're going to take a look at our differences to see if we can write an equation for this graph. All right, taking a look at first differences, to get from 1 to 2, I'm adding 1. To get from 2 to 5, I'm adding 3. To get from 5 to 10, I'm adding 5. And to get from 10 to 17, I'm adding 7. All right, once again, you will see that our first difference is not the same. So this is definitely not a linear function. I'm going to look at my second differences now. To get from 1 to 3, that's like adding 2. 3 to 5, adding 2. 5 to 7, adding 2. All right, so here it is the same. And again, since our second difference is the same, this implies that it is quadratic. Quadratic, again, means there is an x squared in our equation. So I'm going to start with the initial equation, y is equal to x squared. Okay, once again, I'm going to kind of commandeer my columns here and take over this column, and we're going to relabel that x squared. Okay, so once again, I'm going to square my x's and see where that gets me. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. Now, we want to compare this column with our y column. How do these two columns compare? Well, to get from 0 to 1, to get from 1 to 2, to get from 4 to 5, to get from 9 to 10, or from 16 to 17, it appears that I'm going to have to add 1. If I add 1 to 0, then I get 1. Add 1 to 1, I get 2. add 1 to the 4, there's my 5. Add 1 to 9, I get 10. And add 1 to the 16, I get 17. And now these two columns are exactly alike. So my equation becomes x squared plus 1. And this would be my equation for this graph. And it is quadratic, again, in nature, due to the x squared term. All right, let's take a look at a different equation. This one is going to require making a um, using a different kind of a scale. I need both negative and positive y's. So again, I'm going to put my y-axis right along here, but I'm going to put my x-axis right along there. And to get from negative 6 up to 58, let's see, I think I'll go by tens up here. So this would be 10, 20, 30, 40, 50, and negative 10, negative 20 here. And that doesn't quite accommodate my 58, but I think we can guess at where that point would go. All right, so 0, negative 6 is going to be right below the negative 5 line. 1, negative 5 would be right here. 2, 2 is going to be just above the line. 3, 21 will be up here. 458 is going to be right up here. Okay, and again, this is a nonlinear function. Okay, let's take a look at our differences and see what we find to see if we can write an equation for this. All right, well, to get from negative 6 to negative 5, that would be adding 1. To get from negative 5 to 2 would be adding 7. To get from 2 to 21, we are adding 19. And from 21 to 58, that's adding 37. Okay, well, these are definitely not the same. So it's not linear. All right, let's check our second differences. To get from 1 to 7 is adding 6. Added to 7 to get 19 would be 12. And to get from 19 to 37 is adding 18. Again, not the same. So it is not quadratic in nature either. All right, so we're going to go one more difference. To get from 6 to 12, you would add 6, and to get from 12 to 18, you're adding 6. So this appears to be the same. And if the third differences are the same, that implies a cubic relationship, meaning when we write our equation, we're going to have an x cubed in it. All right? Now, I'm going to erase this so again I can use my columns for something else. And let's take a look. We'll use this column. We're going to let that be our x cubed column. All right, so 0 cubed is still 0. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. And 4 cubed is 64. All right, well, we want to compare our x cubed column with our y value. And we'll see that they're not exactly the same. However, if I look to see, well, what would I do to get from 0 to negative 6? I would be subtracting 6. That would give me negative 6. To get from 1 to negative 5. If I subtract 6 from 1, that gives me negative 5. And it appears that in every case, to get from 8 to 2, if I subtract 6, that gives me the 2. And the same, 27 minus 6 gives me the 21. And 64 minus 6 gives me the 58. So now you can see that our y column is the same. So all we have to do to change our equation is to subtract 6. And now we have an equation to represent this function. Now, one of the interesting things about this, and we'll call it what it is a cubic function, is if I had negative x values, you're going to find that this curve would go on down this way. And this is what a cubic function looks like. All right, so a little summary of what we've done. If the first difference, and this would be the difference in your y, is the same, then it's linear. If the second difference is the same, then it's quadratic, which means x squared, and nonlinear. If the third difference is the same, then it is cubic, or nonlinear. And if it forms a V shape, then it is an absolute value function. And I have one more graph I think I skipped, so we're going to go back and do that. And I'm going to add a blank page for this one. All right. This is not on your notes, but just watch and pay attention so that you will see what this looks like and be able to recognize it for what it is if you have a problem along this line. I'm going to just make a quick table of x and y values. Let's see, we have negative 1, 2, 0, 1, 1, 0, 2, 1, and 3, 2. All right, so on our graph, because I have some negative numbers, I'm going to make this my x-axis right here, and I'm going to put my y-axis kind of here in the middle. All right, so graphing these numbers, negative 1, 2 is right here, 0, 1, 1, 0, 2, 1, and 3, 2 are our points. And joining them from left to right, it makes a V shape. When you have a V shape, this is an absolute value function. And if the parent function, if you call it, or the kind of the generic function would be y is equal to the absolute value of x. Well, what we see is when we look at our graph that negative 1, if I take the absolute value, I just get positive 1. What I want is an absolute value of 2. So if I take negative 1 minus 1, I get negative 2. And the absolute value of negative 2 is positive 2, which is what I'm looking for. 0 minus 1 is negative 1. And the absolute value of negative 1 gives me positive 1. 0 minus 1 is negative 1. And the absolute value of negative 1, let's see, I'm sorry, 1 minus 1 is 0. Let me erase this. That looks like Greek. All right. 0, no, excuse me, I'm starting to do it again. 1 minus 1 is 0. The absolute value of 0, of course, is 0. Starting with my x, 2 minus 1 is 1, and its absolute value is 1. And 3 minus 1 is 2. and its absolute value is 2. So my equation, you will see, becomes x minus 1, and the absolute value of that will give you y. Now, this is just a very rough introduction to absolute value functions and writing an equation for them. I'm not going to expect you to write an equation for an absolute value function, but I wanted to introduce that to you. All right. Your assignment is to do page 250. All right, your assignment is page 250. And again, I'd like you to do the odd numbered problems 9 through 19. I encourage you on your graphs to use graph paper. This will make your assignment 10 times easier and your graphs much more readable. If you have any questions, please bring those to class on Thursday. Thank you very much.